All right, welcome to lab and experiment number 13, the investigation of a chemical bond by IR spectroscopy. What we're going to do is talk a little bit about resonance structures, which are some of the things that you've dealt with in your lecture work, and also the IR machine. We're just really, the lab is very simple. You're just going to take the IR of three different compounds, maybe four. Haven't decided yet if it's going to be three or four. You're going to take them and you're going to try to rate them as to which one has the strongest carbon oxygen double bond in them. And essentially, any compound that has resonance structures that would take away from the carbon oxygen double bond would be ones that would be likely to have a weaker carbon oxygen double bond. So if you can create a bunch of significant resonance structures that take away from the carbon oxygen double bond, then that bond's going to be weaker. So we're going to talk about the parameters that make that happen based upon a fictitious compound. Then you'll be given some compounds in class. I'll give you the names of them and the formulas of them. And you can work on drawing some resonance structures and you can make the decision based upon that. So if you just look at a general carbon oxygen double bond in a compound with an R group, and we're going to call it a Z group over here for lack of a better term, because we're going to look at what this Z group is in terms of making our compound either less stable in terms of its carbon oxygen double bond, or more, or not necessarily more stable, but nothing that would take away from it. So the basic resonance structure that you can draw for every one of these is going to be move a pair of electrons up from the carbon to the oxygen and put a negative charge up here and leave a positive charge on this C. Then the question is, whatever this Z group is over here, will it be able to make some resonance structures, or are there features here that are going to make this pull electron density away from this? And if they do, then that makes those resonance structures significant. And if those resonance structures are significant, then it turns out that those compounds would have weaker carbon oxygen double bonds. Now, if we go back to the original scenario on this, essentially we're a factory that makes a lot of perfume type compounds, and a lot of those do have carbon oxygen double bonds in them. And essentially, we want a way to look at various compounds so that if we investigate those compounds, uh, our job is to determine whether or not, if there's a way to estimate those vibrational frequencies, because the stronger the double bond in those cases, um, it would turn out that the vibrational frequencies of them, the stronger they are, it's just an easier way for us to identify different types of compounds according to them. Uh, so, in other words, what you want to know is, can you estimate the vibrational frequency of a double bond, its relative position based upon the strength of its double bond? And the rule would be, the stronger the double bond, the higher the frequency that it would have in terms of wave numbers. So something with a 1700 wave number has a stronger carbon oxygen double bond than something with a 1630 number, wave number. So that's what we're looking for. All right, so we've given you the basics of this. We've given you the scenario. So what kinds of things then would, in essence, mess us up? So if we go and we look at the things that could go into this, let's just take a real compound. Here's one with a carbon-carbon double bond next to our C double bond O. So there's that. We moved up the pair of electrons, put the positive charge here. But if you'll notice, there's a significant resonance structure by moving this pair of electrons over and moving the positive charge out to here, you can see that we've created two resonance structures that take away from the carbon-oxygen double bond. So we would expect these two to be more closer to the 1600 end than the 1700 end if this weren't possible. Other structures that can do that is if this group is, for example, has some lone pairs on it, like nitrogens or oxygens. So we move our pair up just like we normally would, and then notice what we can do. We can bring that lone pair of electrons in from the nitrogen here, create the double bond there, and now put the positive charge here. So now we've created another resonance structure that takes away from this ability. So what kinds of things would leave this thing good? If you just had like a methyl group here or an ethyl group, something that just has some carbon and some hydrogens that are not electronegative and pull the electron density away from the carbon-oxygen double bond, but just have some extra electrons available that would give them back to that sort of resonance stabilizes this. So things with just like a CH3 group or a long carbon chain here would be things that would give you, for example, those would be like ketones. This is a, in this case, it's what's called an amide, and the amide has an N group here. If you put something here, it turns out that if you put something on there like an oxygen, it really doesn't do much at the point of attachment. It really will not. You can disregard the effect of the resonance structures. If it turns out above nitrogen, it really doesn't have much of an effect. But if you have oxygens over there, it still would be not as much of an effect, but it still would be somewhat of an effect as if an oxygen wasn't there. But in that case, we'll probably try to avoid compounds that have the oxygen there to mess you up. So you're going to be looking for things like this, where you'd have the N there to pull things away, double bonds there to pull things away, where you can draw these resonance structures for it. If you really can't draw a significant resonance structure for it, in that case, then it turns out that you probably are not going to have something that's going to be able to pull that away from it. So, but if there is an oxygen there, they typically, in those cases, if you have atoms there that could donate some electrons back to it, then it might also be able to put something there for you that would make it more attractive or stronger, as we would say. So the kinds of things that would be attached to this that would be perfect would be just like methyl groups of this Z group. The next best thing would be an oxygen or something like a chlorine, maybe, that have high electronegativities here. It turns out that anything above nitrogen here has a tendency to not have the effect like nitrogen would. So that kind of a thing would be what you would be looking for in those cases. Anything that, what else would we be looking for? Aldehydes, for example, wouldn't have much of an effect because there's just an H there. It wouldn't take away, it wouldn't add to it. So kind of if we looked at a list of things that would be, if we looked at things that would be good, so just your carbon chains would probably be the best. Aldehydes would have little to no effect, more than likely. And then groups that probably would give you a little bit extra to it would be certain substituents that well, beyond what we've talked about, really, then we get into things that are probably beyond what we are doing. So that's really the whole thing. Take an IR,